Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about the module Electromagnetic Waves 2 from the paper Electromagnetic Theory. So in this module, we continue to study, or rather we continue with the study of propagation of the electromagnetic waves, and you may get to know about the following. Firstly, you will get to revise and understand the reflection and refraction of the electromagnetic waves at the interface between two media. Then we'll discuss the kinematic properties like the geometrical relations between the angles of incidence, reflection and refraction. After that, we'll move on to discussing the dynamic relations like the intensity of the reflected and the refracted components of the wave. After that, we'll discuss the phenomena of polarization of an unpolarized incident wave after reflection and refraction. Conditions for total internal reflection of an incident wave would then be discussed subsequently. So, let us first look at the reflection and refraction of the electromagnetic waves. So in this module, we study the reflection and refraction of the electromagnetic waves at a plane interface between two dielectric materials, the most familiar phenomena in optics. In the debate over the nature of the light, the phenomena of reflection and refraction played a big role. Newton developed and championed his corpuscular hypothesis, arguing that the perfectly straight lines of reflection demonstrated light's particle nature. Newton's contemporaries Robert Hooke and Huygens and later Fresnel mathematically refined the wave viewpoint. The discovery of double-slit interference was the beginning of the end of the particle light camp. And then came Maxwell's equations, which had a wave-like solution with a speed equal to the speed of light. And finally, the explanation of both the kinematic and the dynamic aspects of the phenomena of reflection and refraction from the first principles marked the end of any debate about the wave nature of light. By kinematic properties of reflection and refraction, we mean the relations between the angle of incidence, angle of reflection, and angle of refraction, etc. And by the dynamic properties, we mean the intensities of the reflected and the refracted waves and phenomenon of polarization, etc. The kinematic properties follow immediately from the wave nature of the phenomenon and the existence of the boundary conditions. The dynamic properties, on the other hand, depend entirely on the specific nature of these boundary conditions. Kinematic properties. Now let us consider two dielectric media having an interface along the plane z is equal to 0. So the medium below this plane z is equal to 0 is denoted by the magnetic permeability mu and the electric permittivity epsilon, and the medium above this plane denoted by z equal to 0 is denoted by the magnetic permeability mu prime and electric permittivity epsilon prime respectively. Then for the medium 1, which is below the plane z is equal to 0, the refractive index of the medium is given by under root of mu times epsilon, and the velocity of the light in this medium is given by v is equal to c by under root mu times epsilon. While the refractive index of the medium 2, which lies above the plane z is equal to 0, is given by n prime and is equal to under root of mu prime times epsilon prime, and the velocity of light in this medium is given by V prime is equal to C by under root mu prime times epsilon prime. Now let us consider a plane wave with angular frequency omega and wave vector k that is incident from the medium 1 onto the interface. So basically what we are wanting to discuss over here are the kinematic properties of the electromagnetic wave or light when it propagates from one medium to another. So at the interface, how does the electromagnetic wave behave, and what are the properties of the light that goes into the medium 2, and what are the properties of the light that gets reflected back into medium 1. Kinematic properties. So now let us define the wave vectors of the refracted and the reflected waves respectively by wave vector k prime and wave vector k double prime, where the wave vector of the refractive wave represents the wave which has gone into the second medium, that is the medium which is above the plane z equal to 0, while the wave vector k double prime represents the reflected wave which is in the same medium as the incident wave, that is medium 1, which is below the plane z equal to 0. Now the unit vector from medium 1 into medium 2 is n cap, and the frequency of all the three waves, that is the incident, the reflected and the refracted waves, is omega. Then we can write down the relation between the magnitude of the wave number and the frequency as the wave number of the incident wave is given by the modulus of the wave vector k, and this is equal to the modulus of the wave vector k double prime is equal to k is equal to omega by v, where omega is the angular frequency of the wave and v is the velocity of the wave in medium 1, and this is equal to omega by c times under root of mu times epsilon. Similarly, the wave number of the refracted wave is given by modulus of the wave vector k prime, and this is equal to k prime, and this turns out to be equal to omega by v prime, where v prime is the velocity of the light in medium 2, that is above the plane z equal to 0, and omega is the angular frequency of this refracted wave, and this can further be written as omega by c whole times under root of mu prime times epsilon prime, where c is the velocity of light in free space or vacuum, and mu prime and epsilon prime are the magnetic permeability and the electric permittivity of that material medium. Now the electric and the magnetic fields of the three waves, that is the incident wave, the refracted wave and the reflected wave, are represented by the following equations. So for the incident wave, we have the electric field vector E is equal to the amplitude of the electric field vector E naught times exponential to the power iota times wave vector k dot product with position vector x minus iota times angular frequency omega times time t. The magnetic field induction vector is given by under root of mu times epsilon times whole times the wave vector k cross product with electric field vector E upon the wave number k, and this is equal to the amplitude of the magnetic field induction vector B naught times exponential to the power iota times bracket open wave vector k dot product with position vector x minus omega times time t bracket close, where the amplitude of the magnetic field induction vector B naught is equal to under root of mu times epsilon whole times cross product of wave vector k with the amplitude of the electric field vector E naught divided by the wave number k, and then this can further be written as, using the above definition of the wave number, as c by omega times the wave vector k cross product with the amplitude of the electric field vector E naught. Similarly, for the refracted wave, we can write down the electric field vector E prime is equal to the amplitude of the electric field vector E prime naught times exponential to the power iota times bracket open wave vector k prime dot product with the position vector x minus omega times time t bracket close. The magnetic field induction vector for the refracted wave is given as under root of mu prime times epsilon prime whole times wave vector k prime cross product with electric field vector E prime upon wave number k prime. And this is equal to the amplitude of the magnetic field induction vector B naught prime times exponential to the power iota times bracket open wave vector k prime dot x prime, that is the position vector x, minus omega times time t bracket close, where the amplitude of the magnetic field induction vector B naught prime is equal to under root of mu prime times epsilon prime whole times the wave vector k prime cross product with the amplitude of the electric field vector E naught prime upon the wave number k prime. And then using the above relation that we had got for the wave number k prime, we can rewrite this equation as equal to c by omega times the wave vector k prime cross product with the electric field vector E naught prime, that is the amplitude. And finally, we can write down the equations of the electric field and the magnetic field induction vector for the reflected waves as the electric field vector E double prime is equal to the amplitude of the electric field vector E naught double prime times exponential to the power iota times bracket open the wave vector k double prime dot product with the position vector x minus angular frequency omega times time t bracket close. The magnetic field induction vector B double prime for the reflected wave is given by under root of mu times epsilon times whole times the wave vector k double prime cross product with the electric field vector E double prime upon the wave number k, and this is equal to the amplitude of the magnetic field induction vector B naught double prime times exponential to the power iota times bracket open the wave vector k double prime dot product with the position vector x minus the angular frequency omega times time t bracket close, where the amplitude of the magnetic field induction vector B naught double prime is given by under root of mu times epsilon whole times the wave vector k double prime cross product with the amplitude of the electric field vector E naught double prime upon the wave number k double prime. And now rewriting the equation for the wave number k double prime, we can get the final answer as equal to c by omega times the wave vector k double prime cross product with the electric field amplitude E naught double prime. The kinematic properties. Now, once we have defined the electric field and the magnetic field induction vectors for the incident wave, the refracted wave, and the reflected wave, then we can discuss the boundary conditions that must be satisfied at all points on the plane and at all times. And therefore, the time and space variation of all fields must be the same at the plane z equal to 0. The reason for this is that if we look at the plane z equal to 0, then we see that the incident wave, the refracted wave, and the reflected wave, all the three have that same point in common on the plane z equal to 0. So what that means is that in order for the electromagnetic wave to get reflected and refracted, it is necessary that at this point where the three waves meet on the plane z equal to 0, the continuity of the different fields, that is the electric field vector and the magnetic field induction vector, should be ensured. And these are what we call as the boundary conditions, that at the meeting point of all the three waves, what is the condition that will govern the electric field and the magnetic field of the three respective waves. So one of the first things that this boundary condition implies is that the frequency for all the three waves should remain unchanged, because at the meeting point all the three waves will have the same frequency, and since at that point all the three waves have the same frequency, therefore the wave frequency of the incident, angular frequency of the incident wave, the reflected wave, and the refracted wave should all be equal. Now, the other boundary condition that we need to impose is that at the meeting point, the incident wave, the refracted wave, and the reflected wave should all have the same phase on the plane z equal to 0. So, if we look at the phase term of the three equations, then we get At z equal to 0, the dot product of the wave vector k with the position vector x at z equal to 0, denoting the phase of the incident wave, should be equal to the dot product of the wave vector k prime and the position vector x at z equal to 0, denoting the phase of the refracted wave, and this should be equal to the dot product of the wave vector k double prime and the position vector x at the point z equal to 0, which denotes the phase of the reflected wave. And this is independent of the nature of the boundary conditions. So as a result, all the three wave vectors must lie in a common plane. Now for any point having position vector r lying in the plane z equal to 0, the unit vector n cap dot r is equal to 0 implies that the cross product of the unit vector n cap with the cross product of the unit vector n cap and the position vector r, which can then be written as n cap times the dot product of the unit vector n cap and the position vector r minus the position vector r times n cap dot n cap, which gives us n cap dot position vector r times n cap minus position vector r, and since n cap and position vector r, the dot product is 0, therefore the final result is equal to minus r, that is the position vector minus r. And similarly we can write the dot product of the wave vector k minus wave vector k double prime with the position vector r is equal to 0. Then this gives us the vector identity, the dot product of the wave vector k minus the wave vector k double prime with the vector triple product involving the cross product of the unit vector n cap with the cross product of the unit vector n cap and the position vector r. Now if we interchange the order of this scalar triple product, where the first term in the bracket which contains the wave vector k minus wave vector k double prime and the cross product between n cap and the cross product of n cap and the position vector r, then we see that in interchanging through a cyclical permutation, we get the term the cross product of the wave vector k minus wave vector k double prime with n cap dot the cross product of n cap and position vector r. Now since from the above relation we have defined n cap dot position vector r equal to 0, therefore from this equation also we can write down that this result comes out to be equal to 0. And similarly we can also write down that the cross product of the wave vector k minus k prime with n cap dot the cross product of n cap cross position vector r is 0, because in all these relations we can through a cyclical permutation get a term which has n cap dot r, and we have already defined that for present scenario n cap dot r gives us 0. So this is the vector form of the kinematic properties of reflection and refraction. The dynamic properties. Now, having discussed the kinematic properties, which was basically the boundary conditions governing the propagation of an electromagnetic wave from one medium to another in terms of the incident wave, the refracted wave and the reflected wave, and how the frequency, the wave vector and the boundary conditions can be defined, we now come on to the dynamical properties of wave propagation between two material medium. So in case of the dynamical properties, we first start with the familiar form of these dynamical properties, which is that if k represents the wave vector of the incident wave and I represents the angle of incidence of the incident wave with respect to the normal to the interface, surface of the interface, while K prime represents the angle of the refracted wave and R represents the angle of refraction with respect to the normal angle of refraction of the refracted wave with respect to the normal to the plane of interference or interface, and if K double prime represents the wave number of the reflected wave and R prime represents the angle of reflection of the reflected wave with respect to the normal to the interface of the two medium, then we know that since the wave number K and the wave number K prime denote the same medium, hence the two wave numbers are equal. So if we write down the dynamical properties can be written as K times sine of I is equal to K prime times sine of R is equal to K double prime times sine of R prime. So now first let us look at the first and the third part of this equation, which basically represent the incident and the reflected wave. Since K and K double prime represent the same medium and as discussed earlier are equal, therefore sine I turns out to be equal to sine of R prime, or in other words, the angle of incidence I is equal to the angle of reflection R prime. Now let us look at the first and the second of these three equations. So here, since K represents the wave number of the medium 1 while K prime represents the wave number of medium 2, therefore we can rewrite these equations as sine of I by sine of R is equal to K prime by K, where I represents the angle of incidence while R represents the angle of refraction. Further writing this ratio of K prime and K in terms of the magnetic permeability and electric permittivity as defined above, we get sine I by sine R is equal to under root of mu prime times epsilon prime by mu times epsilon, and this is equal to n prime by n, where n prime is the refractive index of the medium 2 and n is the refractive index of medium 1, and this is what is the popularly known as Snell's law. Dynamical properties. Now let us come on to the dynamical properties of this system which contains two mediums. So for determining the dynamical properties, one needs the specific boundary conditions which are given by that the normal components of the electric displacement vector and the magnetic field induction vector are continuous, while the tangential components of the electric field vector and the magnetic field vector are continuous. So these boundary conditions at the interface, that is at z equal to 0, lead to the following equations. The first equation is in terms of the normal component of the electric displacement vector being continuous, and this gives us that the amplitude of the electric displacement vector of the incident wave plus the amplitude of the electric displacement vector of the reflected wave minus the amplitude of the electric displacement vector of the refracted wave whole times the dot product with the normal vector n cap, unit normal vector n cap, is equal to 0. And from this equation then one can write down, because if one writes the electric displacement vector in terms of the electric field vector, then one can write down this equation as bracket open epsilon times the amplitude of the electric field vector of the incident wave plus the amplitude of the electric field vector of the reflected wave bracket close minus epsilon prime times the amplitude of the electric field vector of the refracted wave whole bracket close dot product with the unit vector n cap is equal to 0. Similarly, writing down mathematically that the normal component of the magnetic field induction vector is continuous, we can write down bracket open the amplitude of the magnetic field induction vector of the incident wave plus the amplitude of the magnetic field induction vector of the reflected wave minus the amplitude of the magnetic field induction vector of the refracted wave bracket close dot product with the unit vector n cap is equal to 0. Now again writing down the magnetic field induction vector in terms of the electric field vector as has been defined above, we can then get the equation bracket open the wave vector of the incident wave k cross the amplitude of the electric field vector incident electric field vector E naught plus the incident wave the reflected wave vector k double prime cross product with the reflected amplitude of the electric field vector E naught double prime minus the refracted wave vector k prime cross product with the amplitude of the refracted electric field vector E naught prime whole bracket close dot product with the unit vector n is equal to 0. Then to write down the mathematically that the tangential component of the electric field is continuous, we write down the amplitude of the incident electric field corresponding to the incident wave plus the amplitude of the electric field vector corresponding to the reflected wave minus the amplitude of the electric field vector corresponding to the refracted wave whole cross product with the unit vector n is equal to 0. And finally, for writing down mathematically that the tangential component of the magnetic field is continuous, we can write down the amplitude of the magnetic field vector of the incident wave plus the amplitude of the magnetic field vector of the reflected wave minus the amplitude of the magnetic field of the refracted wave whole cross product with the unit vector n gives us 0. So again replacing the magnetic field vectors using the relation of these with respect to the electric field vectors, we get bracket open 1 upon mu times bracket open cross product of the incident wave vector with the amplitude of the electric field vector of the incident wave plus cross product of the refractive wave vector with the amplitude of the electric field vector of the refracted wave bracket close minus 1 upon mu prime times cross product of the reflected wave vector with the amplitude of the electric field of the refracted wave whole bracket close cross product with the unit vector n is equal to 0. So basically these four equations simply represent the four boundary conditions that the normal component of the displacement vector is continuous. The second equation gives us that the normal component of the magnetic field induction vector is continuous. The third equation gives us that the tangential component of the electric field is continuous. And the fourth equation gives us that the tangential component of the magnetic field is continuous. Polarization normal to the plane of incidence. Now, it is convenient to consider two linear polarization states of radiation separately. Situation for any arbitrary polarization can be obtained by a linear combination of these two linear polarization states. So let us first define the wave vector k and the unit normal vector n prime, which define the plane of incidence. Now for polarization perpendicular to the plane of incidence, we have that all the electric fields are shown directed away from the viewer if one looks at these figures. So the electric field is normal to the plane of incidence implies that the dot product of the amplitude of the electric field vector of the incident wave with the unit normal is equal to the dot product of the amplitude of the electric field of the reflected wave with the unit normal, and this is equal to the dot product of the amplitude of the electric field of the reflected wave with the unit normal, and all these three turn out to be equal to 0. Since the electric field is normal to the plane of incidence and the unit normal vector is in the plane of incidence. Now, since the electric field is perpendicular to the wave vector k, therefore the unit normal n cap, or in other words what one is wanting to say is that since the electric field vector E of the incident wave is perpendicular to the wave vector k of the incident wave and the unit normal n cap. Therefore, what follows is that the cross product of the unit vector n cap with the incident wave vector k is along the direction of the electric field of the incident wave. And from this one can then write down that the cross product of the incident wave vector with the amplitude of the electric field of the incident wave and the dot product with the unit normal n cap then be written as, with a circular permutation, as the dot product of the electric amplitude of the electric field of the incident wave with the cross product of the unit normal n cap and the incident wave vector k, and this is equal to the amplitude of the electric field E naught times the wave number k of the incident wave times sine of angle I, which is the angle of incidence. And in a similar fashion, we can define for the reflected wave also that the cross product of the reflected wave vector k double prime and the amplitude of the reflected electric field vector E naught prime and the dot product of this with the unit normal n cap is equal to the amplitude of the electric field vector of the reflected wave E naught double prime times the reflected wave number k double prime times sine of I, where I is the angle of incidence, and this is also equal to the angle of reflection, that is r prime. And this is equal to the amplitude of the electric field of the reflected wave E naught double prime times the wave number k of the incident wave times sine of the angle of incidence. Again, since the wave number of the incident and the reflected wave is the same, because the material medium is the same. Now, for the refracted wave, the cross product of the wave vector of the refracted wave and the amplitude of the electric field of the refracted wave and the dot product of this with the unit normal is equal to the amplitude of the refracted electric field E naught prime times the refracted wave number k prime times cos of the angle of refraction, and this turns out to be equal to the amplitude of the refracted electric field E naught prime times the incident wave number k times sine of I, and here we have used the kinematic property or the Snell's law, which is basically that by sine of r is equal to k prime by k, where sine of I is the angle of incidence, sine of the angle of incidence, and sine of r is the angle of refraction, and k prime is the wave number of the refracted wave and k is the wave number of the incident wave. Polarization normal to the plane of incidence. Now, having defined the above equations, we can then write down the equation for the amplitude of the electric field of the incident, the reflected and the refracted wave as E naught, amplitude of the electric field of the incident wave, plus E naught double prime, the amplitude of the electric field of the reflected wave, minus E naught prime, the amplitude of the electric field of the refracted wave is equal to 0. Further, we can also write down the cross product of the incident wave vector k with the amplitude of the incident electric field E naught and the cross product of this with the unit normal n cap as given by these two equations A and B, which are defined as the Fresnel's relations, basically give the ratio of the amplitude of the electric field of the refracted wave to that of the incident wave and the ratio of the amplitude of the electric field of the reflected wave to that of the incident wave. So in that sense, these two relations are extremely important because they give us, in a way, the ratio of the amount of energy that is transmitted to the amount of energy that is reflected. Polarization in the plane of incidence. Now let us look at the other situation where the polarization is in the plane of incidence. That is, in this case, the electric field vector E, the unit normal n, and the wave vector k are all in the same plane. So if the unit vector t is the unit vector in the plane of incidence, then this is perpendicular to the unit normal n prime. Similarly, if u prime is the unit vector perpendicular to the plane of incidence, then the unit vector u cap is perpendicular to the above three quantities that we have just described. Now, for such a case where the polarization is in the plane of the incidence, we write down the amplitude of the incident electric field dot product with the unit normal is given as E naught times sine of angle of incidence, where E naught is the amplitude of the electric field of the incident wave. Similarly, the cross product of the amplitude of the electric field of the incident wave and the unit normal n cap is given by u cap times the amplitude of the electric field of the incident wave times cos of angle of incidence. Further, the cross product of the incident wave vector k and the amplitude of the electric field of the incident wave and its dot product with the unit normal n is equal to 0. The reason being that since all the three quantities, that is the electric field of the incident wave, the unit normal and the wave vector of the incident wave, are in the same plane, so a cross product of any of these two quantities will give a vector which is perpendicular to all the three vectors. Hence, we get a 0 over here. And finally, the cross product of the incident wave vector k with the amplitude of the electric field of the incident wave and its cross product with the unit normal n gives us the result t cap times the incident wave number k times the amplitude of the electric field of the incident wave. Now, the boundary conditions that we had defined above, using those boundary conditions, particularly equation 1, which defined the boundary condition of the electric displacement vector, which said that the normal component of the electric displacement vector is continuous, we can then write down that equation in terms of the relations that we've defined above as epsilon times bracket open the amplitude of the electric field of the incident wave plus the amplitude of the electric field of the reflected wave bracket closed whole times sine of the angle of incidence minus epsilon prime times the amplitude of the electric field of the refracted wave times sine of angle of refraction is equal to 0. And this gives the relation under root of epsilon by mu times bracket open amplitude of electric field of the incident wave plus amplitude of the electric field of the reflected wave bracket close minus under root of epsilon prime by mu prime times the amplitude of the electric field of the refracted wave is equal to 0. So basically we have just used the above relations to rewrite this equation in terms of the electric permittivity and the magnetic permeability of the two media. Further, from equation 3, which defined the boundary condition of the electric field vector, that is, which said that the tangential component of the electric field is continuous, we get the relation using the above equations as bracket open the amplitude of the electric field of the incident wave minus the amplitude of the electric field of the reflected wave bracket close whole times cos of the angle of incidence minus the amplitude of the electric field of the refracted wave times cos of the angle of refraction is equal to 0. The other equations regarding the boundary conditions, that is the equations involving the magnetic field induction vector B and the magnetic field H, do not give any extra results. Polarization in the plane of incidence. Now, solving the above two equations that we have obtained using the boundary conditions on the electric displacement vector and the electric field vector and utilizing the equations that we have derived for polarization of the electric field in the plane of incidence, we can then finally write down the Fresnel's formula involving the electric field, amplitude of the electric field of the incident wave amplitude of the electric field of the reflected wave and amplitude of the electric field of the refracted wave. So the ratio of the amplitude of the electric field of the refracted wave to that of the incident wave is given by the relation twice of cos of incidence, angle of incidence, by bracket open cos of angle of refraction plus under root of mu prime epsilon prime by under root of mu times epsilon prime by under root of mu prime times epsilon times cos of angle of incidence bracket close, and this can then further be written as equal to twice of the refractive index of the medium 1 times the refractive index of medium 2 times cos of angle of incidence upon bracket open mu by mu prime times the refractive square of the refractive index of medium 2 times cos of angle of incidence plus the refractive index of medium 1 times under root of square of the refractive index of medium 2 minus square of the refractive index of medium 1 times square of the sine of angle of incidence bracket close, while the ratio of the amplitude of the electric field of the reflected wave and the amplitude of the electric field of the incident wave is given by cos of angle of incidence minus under root of mu prime times epsilon by mu times epsilon prime whole times cos of angle of refraction whole divided by bracket open cos of angle of incidence plus under root of mu prime times epsilon by mu times epsilon prime whole times cos of angle of refraction, and this can then further be solved to give, if we use the refractive index of medium 1 and medium 2, then we get the relation mu by mu prime times square of the refractive index of medium 2 times cos of angle of incidence minus refractive index of medium 1 times under root of refractive index of medium 2 minus square of the refractive index of medium 1 times square of the angle of incidence whole divided by mu prime times square of the refractive index of medium 2 times cos of angle of incidence plus refractive index of medium 1 times under root of square of refractive index of medium 2 minus square of refractive index of medium 1 times square of sine of angle of incidence. So these two formulae give the Fresnel's relation, that is the relation C and D give the Fresnel's relation for polarization in the plane of incidence. And like mentioned earlier, that these ratios of the amplitudes of the electric field of the reflected to incident wave and refracted to incident wave are important because they again the square of these give us the idea of the energy transmitted and the energy reflected. Further, if the angle of incidence I is equal to 0, then there is nothing to distinguish between the two cases, and both these sets of equations reduce to the ratio of the amplitude of the electric field of the refracted wave to that of the incident wave becomes equal to twice upon under root of mu epsilon prime by mu prime epsilon plus 1, and this is equal to twice of the refractive index of medium 1 upon the sum of the refractive index of medium 1 and medium 2. Similarly, the ratio of the amplitude of the electric field of the reflected to the incident wave becomes 1 minus under root of mu prime times epsilon by mu epsilon prime whole divided by 1 plus under root of mu prime times epsilon upon mu epsilon prime, and this turns out to be equal to the refractive index of medium 2 minus the refractive index of medium 1 upon the refractive index of medium 2 plus the refractive index of medium 1. Here the last forms are for the case where mu prime is equal to mu naught, and which is usually encountered in the case of dry electrics. Polarization by reflection. Polarization by reflection. So from now on, we can restrict ourselves to the case where both the material medium that we are considering, the magnetic permeability for them, that is mu, which is the magnetic permeability of material medium 1, is equal to mu prime, which is the permeability of the material medium 2, and this is equal to mu naught, which is the magnetic permeability of free space. Then from the equation B, we see that for the case of polarization perpendicular to the plane of incidence, the reflected amplitude is never zero. However, for the polarization parallel to the plane of incidence, there is an angle of incidence called the Brewster's angle at which there is no reflected wave. From equation D, this happens when the refractive square of the refractive index of medium 2 times cos of angle of incidence is equal to the refractive index of medium 1 times under root of the square of the refractive index of medium 2 minus the square of the refractive index of medium 1 times square of the sine of angle of incidence. And from this it follows that the angle of incidence subscript B, which is called as the Brewster's angle, so at this angle of incidence, the tan inverse of the refractive index of medium 2 divided by the refractive index of medium 1, that is, we can define this angle of incidence as the Brewster's angle as being equal to the tan inverse of the ratio of the refractive index of medium 2 to medium 1. And from this it follows that the angle of incidence at the Brewster's angle plus the angle of refraction at the Brewster's angle is equal to 90 degrees. So, at the Brewster's angle, the reflected and the refracted waves are exactly at right angles to each other. For reflection from lighter or denser to a denser or lighter medium, this angle is greater or lesser than 45 degrees respectively. The reflected radiation will completely be plane polarized with the polarization vector perpendicular to the plane of incidence. Rather inefficient method of producing plane polarized light, as we have discussed above. The reflected beam is partially polarized even at other angles. Total internal reflection. Now let us consider this special case where the refractive index of medium 1 is greater than the refractive index of medium 2. That is, where the incident wave is in a medium which is denser than the medium in which the refracted wave goes. So for such a case where the electromagnetic wave propagates from a denser to a rarer medium, let us look at what happens, because this leads to a very interesting phenomena which is known as total internal reflection. So in this case, we see that since the refractive index of the incident of medium 1 is greater than that of medium 2, therefore the angle of refraction R is greater than the angle of incidence I. So if we write down the Snell's law, then we get sine of angle of incidence upon sine of angle of refraction is equal to n prime by n, where n prime is the refractive index of medium 2 and n is the refractive index of medium 1. Now let us look at this particular case where the angle of refraction becomes equal to 90 degrees. Now this can always happen because if we go on increasing the angle of incidence, and since in this present case we have seen from Snell's law that the angle of refraction will always be greater than the angle of incidence, so for a particular value of angle of incidence, the angle of refraction will become equal to 90 degrees. And this angle of incidence for which the angle of refraction becomes equal to 90 degrees is called the critical angle of incidence and is denoted by I subscript C. So for this special case of angle of refraction becoming equal to 90 degrees, we see that we can find out the angle of incidence as I is equal to I subscript C is equal to sine inverse of the refractive index of medium 2 divided by the refractive index of medium 1, where IC is the critical angle of incidence for which the angle of refraction is equal to 90 degrees. Now what this means physically is that there will be no flow across the surface, that is, the electromagnetic wave will not flow into the second medium, and which in other words implies that there is going to be a total internal reflection. So for any value of angle of incidence greater than this critical value of angle of incidence, sine of angle of refraction becomes greater than 1, which is not possible, and the cos of angle of refraction then is given by j times under root of sine of angle of incidence by sine of angle of incidence, the critical angle of incidence, whole square minus 1, where j is under root of minus 1 and j is the imaginary term. So from this equation one sees that for angle of incidence I becoming greater than the critical angle of incidence, the sine and the cos term becomes complex, and then we can say that from the phase factor we have e exponential to the power j times k prime dot x, where j is under root of minus 1, vector k prime is the wave vector of the refracted wave, and x is the position vector, and this can be written as exponential to the power j times the refracted wave number k prime times bracket open x times sine of the refractive angle of refraction plus z times cos of angle of refraction bracket close, and this is equal to exponential to the power minus wave vector of the refracted wave k prime times bracket open square of the angle of sine of the angle of incidence to sine of the critical angle of incidence minus 1 whole bracket close whole to the power half times z, this whole being multiplied by exponential to the power j times wave number of the refracted wave k prime times sine of angle of incidence by sine of the critical angle of incidence whole times x. Here it is important to note the refracted wave is propagated only parallel to the surface and is attenuated exponentially beyond the interface, which can be seen from the above equation. This attenuation occurs within a very few wavelengths of the interface, hence one can say that while the refracted wave does penetrate into medium 2, but as such there is no propagation of the energy into the medium 2. Total internal reflection. Now from the above discussion it is clear that while the electric field exists on the other side of the surface, that is, that while the electric field does penetrate into medium 2 for angle of incidence equal to or greater than the critical angle of incidence, however, there is no flow of energy across the surface, and this phenomena is called the total internal reflection. And this can also be seen from the fact that let us look at the Poynting's vector. So if we take the dot product of the Poynting's vector with the unit normal n cap, then this is equal to half of the real part of the dot product of n cap with the cross product of the electric field of the refracted wave and the complex conjugate of the magnetic field of the refracted wave. And this turns out to be equal to c square by twice of omega times mu whole times the real part of dot product of the unit normal n cap with the wave vector of the refracted wave times the square of the modulus of the amplitude of the electric field of the refracted wave. But we know that the dot product of the unit normal n cap with the wave vector of the refracted wave k prime is equal to k prime times cos of the angle of refraction, which is purely imaginary. So the real part of this would give us 0, and therefore the dot product of the Poynting's vector with the unit normal n cap also gives us 0, which in other words again proves that there is no flow of energy. Now let us do a detailed analysis of the electric field perpendicular to the plane of incidence case. Here, since the magnetic permeability of medium 1 is equal to the magnetic permeability of medium 2, therefore the equation B that we had defined above, which was basically the Fresnel's relation for the case polarization normal to the plane of incidence, which defined the ratio of the electric field of the reflected wave to that of the incident wave, that is the amplitude of the electric field of the reflected wave to that of the incident wave. And with this condition that mu is equal to mu prime, this relation gets modified to the following: refractive index of the medium 1 times cos of angle of incidence minus under root of square of the refractive index of medium 2 minus square of the refractive index of medium 1 times square of the sine of angle of incidence whole divided by the refractive index of medium 1 times cos of the angle of incidence plus under root of square of the refractive index of medium 2 minus square of the refractive index of medium 1 times square of the sine of angle of incidence. And this can then be written as cos of angle of incidence minus j times under root of sine square angle of incidence minus square of the refractive index of medium 2 by square of the refractive index of medium 1 whole divided by cos of angle of incidence plus j times under root of sine square angle of incidence minus square of the refractive index of medium 2 divided by square of the refractive index of medium 1. Now from this relation we see that if we take the modulus ratio of the amplitude of the electric field of the reflected wave to that of the incident wave, then the terms containing the imaginary part, that is j, which is equal to under root of minus 1, both in the numerator and the denominator get cancelled out, and what is left is only cos of angle of incidence divided by cos of angle of incidence. Therefore, the modulus of the amplitude of the electric field of the reflected wave divided by the amplitude of the electric field of the incident wave is equal to 1, as was anticipated. The reason being that since there is no flow of energy, therefore all the energy gets reflected back into the same medium. However, the phase changes on reflection, and we can write the numerator as e to the power minus j of phi. Then the amplitude of the electric field of the reflected wave is equal to the amplitude of the electric field of the incident wave times exponential to the power minus twice of j times phi, where j is equal to under root of minus 1 and phi is the phase change. And from this equation, phi can be written as tan inverse bracket open under root of sine square angle of incidence minus square of the refractive index of medium 2 divided by square of the refractive index of medium 1 whole divided by cos of angle of incidence. Total internal reflection. Detailed analysis of electric field in the plane of incidence. So now let us look at equation D, which represented the case of polarization in the plane of incidence and gave the Fresnel's formula for the ratio of the electric field, amplitude of the electric field for the reflected wave to that of the incident wave. So for this case, we see that if we put mu equal to mu prime, then the ratio of the amplitude of the electric field of the reflected wave to that of the incident wave is equal to square of the refractive index of medium 2 times cos of angle of incidence minus the refractive index of medium 1 times under root of square of refractive index of medium 2 minus square of refractive index of medium 1 times square of the sine of angle of incidence whole divided by square of the refractive index of medium 2 times cos of angle of incidence plus refractive index of medium 1 times under root of square of the refractive index of medium 2 minus square of the refractive index of medium 1 times square of the sine of angle of incidence. And this is equal to cos of the angle of incidence minus j times ratio of the square of the refractive index of medium 1 to that of medium 2 whole times under root of sine square angle of incidence minus square of the ratio of the refractive index of medium 2 to that of medium 1 whole divided by cos of I plus j times square of the refractive index of medium 1 divided by square of the refractive index of medium 2 whole times under root of sine square angle of incidence minus square of the ratio of refractive index of medium 2 divided by that of medium 1. Here again, if we take the modulus of the ratio of the amplitude of the electric field of the reflected wave to that of the incident wave, then we see that the imaginary term occurring in both the numerator and the denominator cancel out, and what is left is only cos I by cos I, which is equal to 1, which is again as expected. However, in this case the phase change is given by the amplitude of the electric field of the reflected wave is equal to the amplitude of the electric field of the incident wave times exponential to the power twice of j times psi, where j is the imaginary quantity under root of -1 and psi is defined as tan inverse within brackets under root of sine square angle of incidence minus square of the ratio of the refractive index of medium 2 to that of medium 1 whole divided by the square of the refractive index of medium 2 divided by the square of the refractive index of medium 1 times cos of angle of incidence whole bracket close. The phases change by unequal amounts. Plane polarized radiation on total internal reflection is returned back with the same intensity but as elliptically polarized radiation, and we can then write down the relative phase difference is, so we write down tan of phi minus psi is equal to tan phi minus tan psi upon 1 plus tan phi plus tan psi, which is the identity, and this after substituting from the above equations we get the result. This is equal to minus of cos of angle of incidence times under root of sine square angle of incidence minus square of the ratio of the refractive index of medium 2 to medium 1 whole divided by sine square angle of incidence. And from this we can write down that twice of phi minus psi is equal to minus twice of tan inverse of bracket open cos of angle of incidence times under root of sine square angle of incidence minus the square of the ratio of the refractive index of medium 2 to medium 1 whole divided by sine square angle of incidence bracket close. So students, let us summarize what we have learnt in this module. Firstly, we learnt about the phenomena of reflection and refraction of an electromagnetic wave when it falls on the interface between two media. We then obtain the kinematic relations between the angles of incidence, reflection, and refraction, and these relations are independent of the state of polarization of the incident wave. We next obtained the dynamic properties, the intensities of the refracted and the reflected waves. These intensities depend on the nature of polarization of the incident beam. It was then explained in detail as to how an unpolarized incident electromagnetic wave gets polarized on reflection and refraction. Finally, the phenomena of total internal reflection and the conditions required for it were discussed. Thank you.